So Komal, other people will be coming, or what is the plan? I don't know.
Yes, sir, they are coming. They are coming.
Okay. So did you saw the second assignment that I posted?
No, sir.
Okay. You can look at it on the Google Classroom.
Okay, okay, sir. I'm doing. Sir, in this assignment also we have to read a paper.
Yes, correct, correct. Yes. But this is a paper by Burley Kemp in 1970. This was the first modern algorithm for factoring polynomials over finite fields. So it was very popular classic paper. So I think you will get some insight how this is done. In fact, in the class I will cover some other algorithm. So that's why I have given this paper as an assignment so that you know what is there. The first time when it was discovered.
Okay, sir.
How much time do you think you will take it to finish this? Maybe 10 days or 7 days?
Actually, sir, we have not gone through the complete paper right now. We have just seen that we need to read a paper and summarize it in terms of computational complexity.
Correct, correct.
So,
So
this the summary will be we will have to more focus on the complexity part of the algorithm.
yes,
Or
yes. So basically, because algorithm is anyway given there, you can think in terms of complexity, how to compute the complexity. What was this was because the first modern paper, so it's really nice to look at it. I think few things you will find in the paper anyway. So it's a good reading actually. So I think if you can finish it in next 10 days, then I can give you another assignment. And in fact, since I have not taken any exam, I am thinking, maybe towards the end of the course, maybe in last two lectures or so, or maybe we can have it outside also. We can try to have some sort of presentation from you, on some other paper or something which you think is interesting. Either I can give you or you can choose. What is a good idea?
Sir, I can. I'm thinking of primes in P paper.
Okay. Okay. Yeah, so I think I'm still building the background, I guess, so I hope in another 2 3 lectures we'll be able to have more background so that we can look at the primes in P paper. So you want to present the primes in P paper?
Yes, sir. I was thinking because it is a recent work and I wanted to go through that paper at least one time.
Okay. And but you want to do all of you want to do it individually, or you want to do it in a group, this presentation?
Sir, we can do it individually.
Yeah, so that will be good actually. If you do it individually, that will be good, Yeah. So I think, similarly, other people can pick up also the paper.
Yes, sir. And sir, regarding the assignment one, I have submitted individual my assignment, and Ashish has submitted individual.
Okay, no problem. I will look at it, no problem. Yeah, so I think I
Yes.
looked at it briefly. Everybody has done correctly. That is okay. So the only thing is that now I have to grade, but I guess so. I think a few assignments and maybe a final presentation will be enough, because it's a graduate level course. So we don't have for undergraduate, like undergraduate courses, we have a lot of exams and so on, right? I mean, it's more research oriented course. So I think if you can actually I don't know how many of you are getting more interest. So if you want, I can also give you something on quantum computational number theory, which is a little bit advanced. But I think, of course, we need to have some understanding of classical computational number theory before we can look into the quantum computational number theory. As there is a book by a Chinese mathematician on that, you can search on quantum computational number theory. You will find a book actually. Maybe a PDF you can download from your. I think you are going to university, right? So you can download it from IIT itself, that book. So something from there, if you can present, this will be nice. And I think if you have interest, and I think depending upon, because there's a lot of job market in quantum computational number theory. There are people are looking for companies are looking for people who have expertise in that area. So if you can do something new there, that will be really nice. So I think keep that thing in mind, that each of you either do a project now. I think because now we have almost 1 month left, so by April end or something, right? If you can work out something, either you implement something. I think that's one, if you are good in programming, or you can actually read a paper and present it actually, rather than writing. Okay, so that will be the good assessment, for you as a final. We are not taking any exam actually. Initially I planned, but I think now that is a better choice. So what do you say about it, right?
Yes, sir. That will be better.
So,
We go for
sir,
presentation for
Yeah.
the project.
Yes, Komal.
sir, for the presentation, which paper we have to choose?
So either you can choose, or I can give, whatever you like. In fact, my interest more is on quantum computational number theory. If some of you can pick up paper there, that would be really nice. So I think that's what I'm saying. You can look at the book on quantum computational number theory. I will put a link there also, not in terms of download, but yeah, I mean the difference actually. See if you can pick up something from that book itself. That is also good. That is also good, because it covers more recent things. Quantum computational number theory is more recent topic, so you will know something new. Apart from that, if you want me to give you a specific paper, I will be happy. You just let me know and I can give you the paper. Or if you want your own choice, that is also up to you.
Okay, sir. Okay, sir.
Okay. So I think something that you can present, understand it, present it, that will be really nice. So I think we will keep it towards the last two lectures of the course, or maybe, outside the lectures, we will see towards the end how the course is going actually, how much time we have. Accordingly we can do that. Okay, but
Yes.
keep this thing in mind, that we will be having a presentation. So if you can implement something, that will be really nice. If you can implement something, if you are good in programming, that will be really nice, because a portion of course, title of the course is computational. So apart from complexity, also sometime implementation is also a very good thing. So you have peri GP access. Unfortunately, because we are not meeting face to face, there are many issues. I think probably we are not having that much enough time to actually go through all the peri GP assignments. But mm, if you have that, for example, whatever thing I am doing, say factoring a polynomial, so maybe on peri GP you can try factoring some polynomials. There are routines, there are libraries available for doing those things. So, but that is one thing using a tool. But on the other hand, can you implement something? That would be really nice, implementing something on your own.
Uh,
And
like,
yeah,
number field save if I implement that kind of thing.
what kind of thing?
Number field save.
Number field CV is there, yeah. Either implementing I think, see, actually another thing is that many of the classical things are already available online, so coding will be available. If you do something in quantum computational number theory, I'm sure that will be really new, you know. So quantum computational number theory, most of the stuff will be new. So Quiskit introduction is available. You can actually look at the Quiskit introduction. I can share some videos with you, on the basics of quantum algorithms, and then you can look at the Quiskit implementation of those things and see if you can understand some of the, or you can understand some of the material from the quantum computational number theory book. That will be really nice. I will be sharing that link today itself, so you can look at it.
Okay, sir.
So, but I think please discuss with me and fix a paper or something for presentation. Okay, so let me share my screen. So remember in the last class, we were looking at finding roots of a polynomial over FQ, and I was giving a probabilistic polynomial time algorithm for root finding by Rabin, which was given in 1980. So, there are two cases for it. One was when Q is odd. So that I discussed already. When Q is odd, what to do? We can factor x cube, x raised per q minus x as x times this, and then we do the GCD computation, and this is how we do the factorization. So and then we used to take any alpha in FQ, substitute it, and do the calculations. Right? So now there is a similar algorithms for when Q is even, or basically Q when the characteristic is even. So let me describe that algorithm today. So okay, so FQ is a finite field with Q number of elements, and we assume that the characteristic is 2. Okay, so now what we do, x raised to power Q minus x, we can factor as x plus alpha plus x plus alpha square plus dot 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 dot. So basically somewhere it will be x plus alpha raised to power 2 raised to power n minus 1, all even powers, times 1 plus x plus alpha plus x plus alpha whole square plus x plus alpha whole raised to power 4 plus 8 and so on, x plus alpha raised to power 2 raised to power n minus 1. Okay, for any alpha in FQ. So then what we do, we compute gx, a new polynomial gx, which is congruent to x plus alpha plus x plus alpha square plus x plus alpha raised to power 4 plus x plus alpha raised to power 2 raised to power n minus 1 mod fx. We reduce it with fx, the polynomial that we want to factor. Okay, and we've put f1 of x as GCD of gx and fx. Okay, now if 0 is less than degree of f1, if degree of f1 is positive and less than the degree of f, then f1x is one factor, right? And the cofactor f2 of x is given by fx divided by f1 of x. And so this is how we can continue and split recursively. So we can assume that fx is square free and product of linear factors. Okay, so let us give you the algorithm. Algorithm is finding roots of monic polynomial fx in fqx. Okay, our assumption is that fx is product of distinct linear factors. So if degree of f is 0, you return the empty list, right? There is no factor, obviously. If degree of f is 1, then return the negative of the constant term, right? But since the characteristic is 2, negative is same thing as positive. So return the constant term. Of fx, right? Now initialize a flag. The flag split found to 0. We initialize it with 0. So while split found is 0, we apply a while loop. Choose alpha in f2 raised to power n randomly. Just like the previous algorithm, we are choosing alpha randomly. Now set t of x is equal to x plus alpha and s of x is equal to t of x. For I is equal to 1, 2, and minus 1, compute t of x is equal to t of x square mod fx and sx is equal to sx plus tx. And this loop will end here. Then you compute f1 of x, which is GCD of fx and this new polynomial sx. Once we have f1x, okay, if 0 is less than degree of f1, is less than degree of f, set split found to be 1. Then recursively call this algo on f1x. Again, do the same thing on f1x. And recursively call algo on the cofactor, which is fx divided by f1 of x, and that's all ending. So this is the algorithm. Let me do an example so that it is clear to you. Okay. So normally I have taken alpha to be a root of irreducible polynomial while constructing fields with certain number of elements. Here I am denoting this by theta. So say F16 is field with 16 number of elements is F2 theta. Okay. So where theta raised to power 4 plus theta plus 1 is equal to 0. Theta is a degree 4 irreducible polynomial over binary field. Now suppose our polynomial that I want to factor is f of x is equal to x raised to power 10 plus theta cube plus 1 x raised to power 9 plus theta plus 1 x raised to power 5 plus theta cube plus theta square plus 1 x raised to power 4 plus theta cube x cube plus theta cube plus theta square plus 1 x square plus theta square x plus theta cube. This belongs to f16x, a polynomial of degree 16. So we compute hx, our polynomial, which is x raised to power 16 plus x modulo fx. So this turns out to be the whole polynomial modulo fx, right? Modulo fx, I can see. So this is theta cube plus 1 times x raised to power n 9 plus theta square plus 1 times x cube plus theta cube plus theta square plus theta plus 1 times x raised to power 7 plus theta plus 1 times x raised to power 6 plus theta plus 1 times x raised to power 5 plus theta times x raised to power 4 plus theta cube plus theta square plus theta plus 1 x square plus theta cube x plus theta cube plus theta square plus 1. All this is modulo fx. We reduce it modulo fx. Look at the remainder. So now replace fx by this new polynomial, which is GCD of fx and hx. Okay, and this turns out to be x square plus theta cube plus theta square plus 1 times x plus theta cube plus theta square plus theta plus 1. Okay, so now we need to factor this. So we try theta randomly. So we try alpha to be the root, say theta plus 1. We have gx is equal to x plus alpha plus x plus alpha square plus x plus alpha raised to power 4 plus x plus alpha raised to power 8, and this turns out to be theta cube x plus theta cube plus theta plus 1 modulo fx. Now split fx as split fx. The splits of actually fx are f1x, the first factor, which is GCD of fx and gx, and this turns out to be x plus theta square plus theta. And f2x, the cofactor is fx divided by f1 of x, turns out to be x plus theta q plus theta plus 1. Therefore, roots are theta square plus theta and theta q plus theta plus 1. Okay, so this is an example which, so here we have a strong assumption on the polynomial fx, that it should be a product of linear factors. Now we can actually get rid of that and we can give better algorithms. As I mentioned earlier, so if we want to factor polynomials over fq, field with q number of elements, many algorithms are known. The first one, the model algorithm, is given by Burley-Camp Q matrix method, and this is the paper which I gave you as an assignment. It is 1970 paper. It's a beautiful paper by E.R. Burley-Camp. Okay, this is the paper which I gave you as a homework. Yes.
Sorry, sir. That was my. I was saying yes. Yes, yes, we have received the.
Okay. Second, version is an algorithm given by Cantor and this algorithm was given in 1981, and this is also a probabilistic algorithm. Okay, and so this is one of the main algorithm. In fact, this algorithm is in 3 steps. We are going to actually describe this algorithm now. Third algorithm was given by Wanzur and Victor Shoup. Victor Shoup, they gave a variant of this algorithm, okay, in 1992. And fourth algorithm is also a faster implementation of this, given by Poltofen and Victor Shoup again. This is 1998, the latest algorithm for factoring polynomials over FQ. Okay, so we are talking about factoring arbitrary polynomials. How do we factor arbitrary polynomials over finite fields with Q number of elements? All these things are quite useful, especially for decoding, BCH codes. There we use all these things, all this material. BCH codes are very important codes. And okay, so the algorithm that I'm going to now describe, so it has 3 stages. So we want to factor arbitrary polynomial. Okay. So the first thing, so there are 3 stages. So I'm going to describe algorithm number 2 by Cantor. Okay, so the first condition is square free factorization. Square free factorization. Okay, so let us see what is square free factorization. So let let fx be a polynomial in fqx. Of course, we are assuming that it's a non-constant polynomial. If it's a constant polynomial, then it's trivial, right? Non-constant polynomial. Okay. Now, write f of x as product of square-free polynomials. Square-free polynomials means factors are not square. Okay, square-free polynomials. So actually, you know how we are going to do this. Let me explain. First, suppose our polynomial fx is of this form: alpha d x raised to power d plus alpha d minus 1 x raised to power d minus 1 plus alpha 1 x plus alpha naught. Now you remember we are working with the discrete space, right, over the finite field. So how do we define derivatives? I mean, so here we can define formal derivative of a polynomial f of x. Formal derivative, we can define it like f dash of x is equal to d times alpha d x raised to power d minus 1. You see the differentiation of this plus d minus 1 alpha d minus 1 x raised to power d minus 2 plus dot 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 2 times alpha 2x, because here somewhere there will be alpha 2x square, that will be 2 times alpha 2x plus alpha 1, because the differentiation of alpha 0 will be 0, which is a constant, right? This is how we define a formal derivative f dash of x. Okay, now I'm going to describe a proposition which is quite good and quite useful. The proposition says like this: f dash of x is 0 if and only if the derivative of fx is 0 if and only if fx is equal to gx raised to power p for some polynomial gx in fqx. Okay, and what is p? P is the characteristic of fq. So we know that q is, say, p raised to power n or something, right? Finite field with q number of elements, right? Q is some prime power. So p is the characteristic of fq. So f dash of, so derivative of fx is 0 if and only if fx can be written as some power of fx can be written as p power of some polynomial gx. Okay. Further, the polynomial fx divided by gcd of fx and f dash of x is square free. The polynomial this fx divided by gcd of fx and f dash of x is square free. I would like to show this. In particular, fx is square free polynomial if and only if gcd of fx and f dash of x is 1. So this is our main result that I would like to prove for you. So there are 3 parts. Part 1, that derivative is 0 if and only if fx is written as p power of some polynomial gx. P is the characteristic of fq. Second, so this is your first part. Second part, the polynomial fx divided by GCD of fx and f dash of x is square free. In particular, fx is square free if and only if GCD of fx and f dash of x is equal to 1. Okay, so let us start proving it. So what we can do here, let us rewrite fx as alpha 1 raised to power x raised to power e1 for some alpha 1 e1, alpha 2 times x raised to power e2. Suppose this is the most general form, alpha k e raised to power, sorry, x raised to power ek. X raised to power ek. Where, the exponents are pairwise distinct. Distinct EIs. Pairwise distinct EIs, and each alpha I is not equal to 0. Otherwise, it doesn't make any sense. Each alpha I is not equal to 0. Then, what I can do, I can compute the derivative of x, which will be e1 alpha 1 x raised to power e1 minus 1 plus e2 alpha 2 x raised to power e2 minus 1 plus dot 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 ek alpha k x raised to power ek minus 1. Right? Differentiation with respect to x will give us this. Now, suppose derivative is 0. Suppose f dash of x is equal to 0. So what I need to show that? Suppose fx derivative is 0. I will show that fx is some power of gx, for some, where p is of course the characteristic of the field. Now, suppose this is 0. So now that means this whole quantity is 0. Right? Now, this implies that each EI, because alpha is not equal to 0, each EI is a multiple of P. Multiple of P, because it is all modulo P, right? Characteristic is P, modulo P, you can think of. So each EI is a multiple of P, right? So then only this will be 0. Alpha is not equal to 0. That means we have EI can be written as P times epsilon I for 1 less than equal to I less than equal to K. For each I, EI can be written as multiple of P, right? For some epsilon I, right? Now, alpha I is an element of fp raised to power n, means fq, right? Q here is p raised to power n. I have assumed it. This implies that alpha I raised to power p raised to power n is equal to alpha I. Remember, every element of the finite field will satisfy this equation for every I, right? So I can substitute all these things together. So I can substitute basically alpha I, replace each alpha I by this. Here in this expression, f dash of x equal to 0, right? I mean, so basically fx will be what? Fx can be written as gx raised to power p, where gx is nothing but alpha 1 raised to power p raised to power n minus 1 x raised to power epsilon 1 plus alpha 2 raised to power p raised to power n minus 1 x raised to power epsilon 2 plus dot 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 alpha k raised to power p raised to power n minus 1 x raised to power epsilon k. because if I raise the whole thing by power p, what will happen? This will be alpha I raised to power, right? This will be alpha I raised to power p raised to power n, which is alpha I, right? So alpha 1 raised to power x raised to power, and p times epsilon is E1, E2, and like so, and so on, right? So we can write it like this. Since characteristic is p, so remember a plus b plus c, whatever z, whatever size is there, raised to power p is same thing as a raised to power p plus b raised to power p, and so on, z raised to power p. Because characteristic of the field is p, you can do this expansion here, right? Because when we expand this multinomial expression, the coefficients will be some choose, and those choose will be congruent to 0 mod p. That's why this expression is there. Hence, when we raised whole raised power p, we are going to get fx, okay, without any problem. Okay, so fx can be written as this. Okay, now, so this is one part. So I have assumed that f dash of x is equal to 0. I have assumed that f dash of x is equal to 0, and I have shown this thing, that fx is gx raised to power p for some p, right? P is the characteristic. Now the reverse part, suppose fx is of the form gx raised to power p. Suppose fx is of the form gx raised to power p. Now this implies that f dash of x will be what? P times gx raised to power p minus 1 times gx, g dash of x, yes. Right. Now this is modulo p will be 0. So this portion is clear. If fx is of this form, then derivative is 0. If derivative is 0, I have shown that fx will be written like this form. Okay. So first portion of the proof is done. The derivative of x is 0 if and only if fx is gx raised to power p. Second and third, I would like to show. So now let fx can be written as, factorization is something like f1 raised to power s1. I'm not writing f1 of x all the time, or maybe the first time I can write it f1 of x, f2 of x raised to power s2, dot 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 fl of x raised to power sl. So suppose it is like alpha times f1, f2, fl. Okay. Suppose this is the factorization of f. This is the factorization of f in monic irreducible factors into monic irreducible factors fi of x with si non is greater than or equal to 1 for every I. Okay. Now we derivative. What will be the derivative of f dash of x will be alpha times s1 f1 raised to power s1 minus 1. पहला टर्म का डेरिवेटिव होगा टाइम्स f1 of prime, f2 raised to power s2, fl raised to power sl, right? पहले का डेरिवेटिव प्लस दूसरे का डेरिवेटिव, दूसरे टर्म का डेरिवेटिव आएगा प्लस अल्फा टाइम्स s2 f1 raised to power s1, f2 raised to power s2 minus 1, f2 prime, fl raised to power sl. right? And so on, dot, 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 plus alpha times SL, last wala term, F1 raised to power S1, F2 raised to power S2, FL raised to power SL minus 1, and F minus 1, and FL prime, right? Product, component wise product हम differentiation हम कर सकते हैं, right? So now once we have this, I can take certain things common here. Alpha times F1 raised to power S1 minus 1, F2 raised to power S2 minus 1, FL raised to power SL minus 1 times S1, F1 prime, F2, F3, FL plus S2 times F1, F2 prime, dot, 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 FL plus dot, 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 SL times F1, F2, FL minus 1, FL prime, right? I have taken these things common, so we are left with this expression. Now this factor, I can write it, the factor in square bracket is divisible by Fix if and only if P divides Si, right? If and only if P divides Si, then it will be divisible, right? Therefore, if I compute the GCD of Fx and F dash of x will be alpha raised to power F1 raised to power T1, F2 raised to power T2, FL raised to power TL, right? Where each Ti is either Si or Si minus 1 according to whether P divides Si or not. Okay, this we can write. That means Fx divided by GCD of F and F prime is a divisor of F1, F2, FL, and is therefore square free. So this important result tells us that actually it gives us a method, how to convert anything into square free factorization. So let me show you how this is useful by an example, right? The result is this proposition. The derivative is 0 if and only if fx can be written as gx is for p for some p, and for some polynomial gx in fqx, p is the characteristic of fqx. The polynomial fx divided by gcd fx f dash of x is square free. In particular, fx is square free if and only if gcd of fx and f dash of x is 1. So we will recursively use this technique to compute. So let me describe the method. How to compute the square free factorization of fx. How to compute the square free factorization of fx. So what we do, fx is given to us, just compute derivative. Okay, compute f dash of x. Now what could happen? If f dash of x is equal to 0, then you compute gx in fq of x such that fx is gx raised to power p or some gx, right? And recursively compute the square free factorization of gx now, right? So this is the case. If the derivative is 0, so again, in this case also, in case of gx also, if the derivative is 0, there are two choices, the derivative is 0, there is, again, you can write gx is equal to, say, hx raised to power p or something, and we do the same thing on hx and so on. If derivative is not equal to 0, then you compute hx, which is GCD of fx and f dash of x. If this GCD is 1, then fx itself is square free. It is square free, right? Otherwise, we output the factor. We output the square free factor actually. Fx divided by hx of fx, and recursively compute the square free factorization of hx. So this is a general method. Let me give you a small example at how this is done. Small example. Suppose f of x is x raised to 16 plus x raised to 8 plus x raised to 6 plus x raised to 4 plus x squared plus 1 belongs to f2x. This implies that f dash of x is equal to 0 because everything is a even thing, right? In fact, you note that fx can be written as gx squared, where gx is nothing but x raised to 8 plus x raised to 4 plus x raised cube plus x squared plus x plus 1, right? Okay. Now you compute g dash of x. Turns out to be x squared plus 1, which is not equal to 0. And then we compute hx, which is GCD of gx and g dash of x, right? And this turns out to be x squared plus 1. This implies that gx divided by hx is equal to x raised to 6 plus x raised to 4 plus x plus 1, which is square free, right? Now compute square free factor of hx is equal to x squared plus 1. Okay. Now we can compute the derivative h dash of x equal to 0. In fact, hx can be written as x plus 1 whole square because characteristic is 2 here. Okay. X plus 1 whole square is same thing as
x square plus 1. So x plus 1 is coprime to its derivative is square free. So fx can be written as x raised to power 6 plus x raised to power 4 plus x plus 1. 6 plus x raised to power 4 plus x plus 1. X plus 1, x plus 1. That's all actually. That's all for today. So we will meet in the next class. Okay.
Okay, sir.
Okay. Thank you.
Okay, sir. Thank you.
Thank you.
हेलो प्रवीण।
हाँ, yes. आपको बोल-
हाँ, मतलब कैसे क्या करना है, ये तो बोल रहे पेपर भी करना है।
अरे ये हम लोग अलग से डिस्कस करते हैं ना, ये रिकॉर्ड होता है, ऑटोमेटिक इनबिल्ट होता है, इसमें शो नहीं होता।
अच्छा ऐसा है क्या? अच्छा ठीक
हाँ।
है।
बाद में कर सकते हैं।